Hello everyone, how's it going? My name is Dan the Tutor. In today's video, we're going to be talking about optimization in Calc 1. So just a fair warning, I think this is the number one hardest topic in all of calculus. The reason for that is because, first of all, it's word problems, which students never like. Second of all, it's a lot of steps. You remember when we did critical points and relative extrema, maximums, minimums? Well, that's just one step. Like all of that is just one step in a 6-step process with optimization. So the best advice I can give you is to practice, practice, practice. There's only a few scenarios that you can be expected to see. I'm going to be showing you a couple of them today. And I'm probably going to make a part 2 to this video too, where I start talking about problems with cost in them, but I'm not going to be going over cost in this video. I'll probably cover it in a different one. So let's start off with honestly just an example problem, and I'll explain the steps as I'm doing it. So I want to build a fence around an area that is bordered by a river at the north end. I'm going to build this fence, which has a length of X and a width of Y, and I want to have an area of 50 yards squared. That's my goal. I want to enclose an area. Maybe I want to hold chickens or pigs or whatever, and I want the area to hold 50 square yards. I also want to, because I'm an economic farmer, I want to minimize the amount of fencing that I'm using to build this enclosure. So the goal, build the minimum amount of fence possible with an area of 50 yards. Okay, so a couple things I can do here if this were not a calculus class. One thing is to do a guess and check where you plug in values of X and Y until you find the best value. Another thing is to realize that this is going to follow a parabola shape, and I guess I'll explain what I mean by that in a minute, but it doesn't matter what I would do in a pre-calculus class. This is calculus, so the way we're going to solve this is as follows. Step 1, I need to come up with an objective and a constraint equation. The objective is the thing that I'm trying to minimize or maximize, in this case, the amount of fencing. I hope you realize that when I say minimize fencing, I'm really talking about minimizing my perimeter, because that's really what the fencing is all about, the perimeter. So the perimeter of this example would be P equals, if you're having trouble here, it's because there's an invisible Y on this side that I'll just fill in. And so therefore the perimeter is X plus 2Y. So that's the perimeter, the objective. And the constraint is always going to be the number next to it. The constraint's going to have the number next to it. So when I have area 50 yards squared here, that is going to be my constraint. Keep in mind, this is also the area of a rectangle, which hopefully you know that. You should if you're in calculus by now. But I'm always amazed at how little my students know. So the area is equal to X times Y. That's the length times width of my rectangle. And that's going to be equal to 50. So step 1's done. I have my objective. I have my constraint. Now step 2 is going to be where I solve for one of my variables here. It doesn't matter if I choose X or Y. I do have to choose the constraint. I cannot solve the objective yet. So I'll just choose to solve for, I don't know, let's say I choose to solve for X. Doesn't matter. Literally doesn't change the problem that much. So X equals 50 divided by Y. And now I can plug that X in right there, back to the objective, the perimeter equation. So this is going to start to be step 3. Step 3 is going to be plug in from my constraint to the objective and start to simplify. So for instance, perimeter equals plugging in for X, which is now 50 over Y, plus 2Y. Normally I would simplify at this step, but I really can't simplify here anymore, which is fine. I'm kind of done then. Sometimes there's a lot more simplifying to do, so I get lucky here. So then finally, step 4, I shouldn't say finally, there's still a couple steps to go, but the next step is finding the critical points, the extrema, and this is going to be a pretty long step, so watch what I'm talking about. First thing we need to do is take the derivative of this. I do not recommend taking the derivative of 50 over y. I do recommend rewriting that as 50y to the negative first, because it's so much easier to take derivatives when you have negative exponents. And then the plus 2y is still there. Great. So the derivative of this, following just a simple power rule, the -1 comes out front, and -1 times 50 is -50. And now that's going to be y to the -2nd power. So I'm going quickly through that because I'm assuming you know this already. Plus the derivative of 2y, that's just going to be 2, easy. And this is going to be set equal to 0. So watch what I do next. The next thing I'm going to do is, in order to solve, this -2nd power is kind of kicking my butt here. I really don't like it. So what I'm going to do is I'm going to rewrite it as -50 over y squared. And now that, I actually moved it back to the denominator. The reason why I'm doing this is because it's easier for me to solve this way. So watch what I do next. It's pretty easy. Subtract 2 from both sides. So now -50 over y squared equals -2. If you're stuck here, that's because you got to multiply both sides by y squared next. And it will look like that. And then I'm going to divide by -2. And that's going to get me now positive 25 equals y squared. When I take the square root, it does look like it's going to be a friendly number. That was just a coincidence. Did not try and make that happen. It's fine if I had a decimal. I have a calculator right next to me for these problems. And you usually do as well. Your teacher usually lets you use a calculator for optimization, usually. Anyways, square root of 25 is going to be 5. And if you say 5, of course you're wrong. It is plus or minus. Like, come on, people. When you take a square root, it should be plus or minus. However, it's not plus or minus because it is just the positive 5. You can't have a negative distance, which is fine. So y equals 5. That's going to be yards as the unit. We're not done yet. Technically, you're supposed to do a number line test. If you forget what that is, first of all, this is where you're plugging in points around 5. Like, for instance, we can test 4, and then we're going to test 6. And you're testing that by plugging it into the derivative function here, this guy here. Or you can even plug it into this version right here of the derivative. That's probably what I'll do. -50 over y squared plus 2. Remember, the reason why we're plugging in points is because you want to validate that we just found the maximum or the minimum. Remember, this question wanted the minimum fencing. I better get a minimum here. If I get a maximum, that's a very quick way to tell me I did something wrong. So -50, I'm plugging in 4 first. 4 squared plus 2. That's going to be -50 over 16 plus 2. I might not know exactly what this is. I do know that if I get a common denominator, it would be -50 plus 2 times 16 over 16 is 32 over 16. Whoops. Yeah, so what I'm trying to say is that it's definitely going to be a negative number. It's going to be -18 over 16. I don't care about the number. I just care that it's negative, and I'm going to put a little negative right there. By the way, another thing worth mentioning, this is kind of a helpful tip more than anything else. I can put a lower bound on this number line. The lower bound would probably be 0 because I can't have a length lower than 0. That means I shouldn't test any negative numbers. You probably weren't going to anyway, but you shouldn't test any number lower than 0. You can, I would not test 0 either in this example because you can't have a fence with a length or a width of 0. So the smallest value I would think is smart is 1 or 0.1 if you really want to do that. But 4 makes sense. If I plug in 6, I'll just do this quickly. I'm not going to actually do the math, but if I plug in 6 like this, I'll just tell you I am going to get a positive. You can believe me if you actually plug it in a calculator or you get a common denominator. Doesn't matter. But that does confirm that 5 is going to be a minimum because we got a negative to a positive in the sign test, which is great because, again, I wanted a minimum. And so that confirms y equals 5 yards is the dimension of at least the width, y, going back to the picture. We know y is 5 now. But now I got to find x. And how am I going to find x? Well, it's actually very easy. All I got to do is look back at this equation right here from my constraint. X equals 50 over y. So all that means is x equals 50 over y is 5, and x is going to be 10. 10 yards for x. Y is 5 yards. I don't even need to check anything for the x. Like, I'm just done. And that's the answer to this question because I just wanted to solve for x and y. Keep in mind, if I actually wanted to find the perimeter of the fence itself, or how many yards of fence I wanted to buy to build this fence, then I would actually be plugging in the formula x plus 2y, and the answer would be 10 plus 2 times 5, and the actual perimeter is 20 yards. I didn't ask for that, but if I did, that's what the answer would be. So hopefully that makes sense. Again, just to quickly go over how we solve this optimization problem. The picture is kind of optional. Obviously, a picture helps. So if they don't give you a picture, I would probably draw one. The first real step is finding the objective and the constraint equations. Remember, the objective is always the thing we're solving for, in this case, perimeter. And the constraint is almost always going to be the thing with the number next to it. And by that, I mean the area was 50 yards squared. After you have the, after you have the objective and constraint equations, next thing you want to do is solve for one of your variables. I chose x. If you chose to solve for y, by the way, y equals 50 divided by x, we would get the same answer, just in a different way. It would just be slightly different steps, but the same process. So anyways, I plug that into the objective. I simplify if I need to. That involved, rewriting this to take the derivative in the next step. But then you take the derivative, set equal to 0, basically find the critical points and extrema from the last unit when we talked about that. And then after you find the minimum, you basically want to plug in, after you confirm that y equals 5 is the minimum, you plug that into the constraint equation, which was here again, and that's how you find the other dimension, x. So hopefully that all made sense. We are going to do one more example today, and this one's going to be a little bit harder for sure. But if you want to try it on your own first, I encourage you to. You can pause the video and give it a try on your own, and then I'll walk you through it. Okay, so here's the second problem. So let's say I have a garden. I want to set up a garden, and this garden is actually going to consist of 2 rectangles. And it's going to make sense why in a second. So I have my 2 rectangles here. It's going to look like this. And the reason why I have 2 rectangles is because the actual garden itself will be in the middle. Okay, there's my garden. Pretty nice. Nice little garden here. And then the outside is actually going to be a walkway. So I can walk around my garden. That makes sense, right? Okay, if you disagree, I don't really care. This is the setup. And here's what I know. I have an 800 square foot area to build the garden and walkway. Like the whole area is 800 feet squared. Now, my question is because even though I have the walkway in the garden, really this is about showing off my garden, of course. So what is the maximum area of the garden I can have? And that's really all I know about this problem. I don't have any other numbers. I don't have lengths here. Actually, I missed one thing. Sorry. I do know that I want to give a clearance of 2 feet on the length side, okay? And 1 foot of clearance on the width side, on each side, like this. By the way, I technically don't know what side is longer. I don't know if the length is longer or the width yet. That's fine, doesn't matter. But I do want to maximize the garden, the red inner rectangle. And if you're stuck, I will give you a hint. The hint is when it comes to the objective and the constraint, right? The objective and the constraint actually is going to depend on what you define as x and y. Let me explain. If you define this as x and this as y, then what's the area of your garden? The area of the garden, which I'll call AG for short, the area of the garden is actually going to be the length, which is x minus 4, because you're subtracting 2 on each side, and then times the width, which is going to be y minus 2, because you're subtracting 1 on each side. Hopefully you see that. If you don't, just try and listen to it again, and if it still doesn't make sense, then we just got to move on, because this is the correct answer. Although there is another thing you can do for this objective equation. The other thing you can do is, and I'm going to write this down, but I don't recommend you write it down if you've been following along, just because it gets pretty complicated pretty quickly. You can also define this distance as x and this distance as y. The reason why you do that is because now the area of the garden is easier. It's going to be x times y. But the trade-off is the area of the entire enclosure is going to be different, because now the entire width is going to be x plus 4, because you're adding the 2 feet on each side. And this width is going to be y plus 2, because you're adding 1 foot on each side. So I'm not going to do it that way. You can do it. Maybe it's easier. I did it the other way because I had a feeling the math would be easier the way I'm doing it right now. But if you disagree with me, then, it doesn't matter. We'll get the same answer at the end of the day. Okay, so the objective, like I just said, area of the garden, which I want to maximize, is x minus 4 times y minus 2. And again, the constraint is going to be the thing with the actual number. That's the 800 right here. So 800 is equal to the area of the entire thing. And the entire thing is x times y. And again, that's the trade-off. My objective is a little bit harder, but my constraint's really easy. And that's going to make my step 2 really easy. Remember, step 2 is where I say, solve for x or y. I solved for x last time. This time I'm going to solve for y. Y equals 800 divided by x. Okay. So then I'm plugging that in right there for y. So that means the area of my garden is quantity x minus 4 times quantity 800 over x minus 2. Great. So at this step, before I take the derivative, it's up to me whether or not I want to FOIL this out. It is optional. If I do not FOIL it out, I will need a product rule. And I generally don't like the product rule. Neither do you, likely. So what I'm going to do instead is I am going to FOIL this before I take the derivative. So x times 800 over x is going to be, the x's cancel, leaves you with 800. X times minus 2 is minus 2x. The middle one is going to be minus 3200 over x. And then the last one, negative 4 times negative 2 is plus 8. Okay, so I'm not even going to simplify this, really. I mean, the only thing I will do, I will rewrite this 3200 as 3200 x to the minus 1 power. The 8 and the 800, I don't even care about. I can combine them very easily. I can make it 808 if I really want to. But it doesn't matter, because when I take the derivative, ag prime, in literally the next step right now, the 800 and the 8 just disappear. They're constants. It doesn't matter. And the derivative is just going to be negative 2 minus, it's actually a double negative because you bring the negative 1 out in front, so it is plus now, 3200x to the negative 2nd power. And that I'm going to set equal to 0. Maybe from here you know how to solve the problem, so go ahead. But I'm going to keep trucking along. You're going to see me do the same thing I did last time. I'm going to rewrite this in the denominator, because that is a very good idea when it comes to solving. Then I'm going to add 2 to both sides of the equation. So 3200 over x squared equals positive 2. If you remember what I do next, I multiply both sides by x squared. And then we divide by 2. That's going to be 1600 equals x squared. And again, did not try and do this, but we get lucky. The square root of 1600 is 40. And I'm just going to write positive 40 this time. I'm not even going to bother writing the negative 40 because it doesn't matter for a real life word problem, right? Because you can't have a negative width or length. So that's going to be x. Again, technically you are supposed to do the number line test. And once again, I'm lower bounding this answer at 0. And here's 40 over here. This problem probably has an upper bound somewhere, but I'm not even going to worry about the upper bound because I don't have an easy way of finding it. And the only reason I'd have to worry about an upper bound is if I'm testing a point like 100, and maybe that's out of bounds, you know what I mean? But if I just test a point close to 40, like let's say I test 41 here, I'm not going to have to worry about the upper bound constraint with the area. And same thing is true if I choose any value between 0 and 40, I'm going to be fine. So between 0 and 40, I'll just choose 10. Literally doesn't matter. And again, I'm plugging that into the first derivative, which was -2 plus 3200 over x squared. I'm testing 10 squared. If you're not allowed a calculator, that's fine. This problem's not that bad. The 2 zeros cancel out, and it's going to be -2 plus 32. And that's definitely going to be a positive number for that section of the number line. So I'll just put a little positive right here. And then if we test a number like 41, it is going to be negative. I'll admit I don't know what 41 squared is, but I do know that it's going to be a bigger denominator. And a bigger denominator basically means that we're going to have a smaller number overall here. 41 squared I can probably do in my head because it's 1600 plus 40 plus another 40 plus 1. So that's 1681 in the denominator. So -2 plus 3200 over 1681. I mean, again, I said this earlier, it's definitely easier if we do this with a calculator, and you probably get a calculator on the test, so I'm not too worried about that. But it is going to be negative here, confirming that. Why were we doing this again? Oh yeah, we were trying to confirm this is a maximum. And now it is, because we got positive to negative, and that's what we're looking for a maximum. So x equals 40 is my maximum. How do I find y again? That's right, kids. You just have to plug it into our constraint. Our constraint was y equals 800 over x. X is 40. Again, we got that at like the very beginning. I'll even scroll back up to show you. It was from the constraint equation right here. That's how you find the other variable. And so 800 divided by 40 is just going to be 20. And so units were feet this time. Be careful, because remember what the question was asking for? We wanted to actually find the maximum area of the garden, okay? So then let me just draw the picture one more time just to illustrate this, okay? So we just said this dimension x was 40, the total. This dimension y is 20. I want to find the area of the middle section here in the garden. And so what that means is this distance, because it was 2 feet taken off on each side, it's actually going to be 36 feet for the length. And for the width, it's going to be 20 minus 2, right? Because it was taken 1 foot off of the top and bottom, leaving me with 18 feet for the width. And so if I want the area of just the garden, it's going to be 36 times 18, or following my other formula, that would have been 40 minus 4 times 20 minus 2, which is obviously the same thing. And I don't want to do this in my head, but I have a calculator somewhere. Here it is. So 36 times 18. Maybe I should be able to do this in my head, but who cares? It's going to be 648. What's the units? That's right, feet squared. Because it's an area, not a volume, not a length, it's area. And so that's going to be the answer for this problem. Now, by the way, we've only looked at 2 examples. There's a ton of examples we can look at for optimization, but this covers a good number of scenarios we're going to see. And really the hardest part of optimization problems is literally the first step, coming up with the objective and the constraint equation, because everything after that is basically the same, like the same thing. We're solving for the constraint, plugging into the objective, simplifying, taking the derivative, finding relative extrema with the number line test, and then answering the question. So that's what we're going to be doing every time for these problems. And really the hardest part is just coming up with that objective and the constraint equation. So one more time, in the next video, I'm going to cover how to do the exact same thing, but we're going to have costs tied to this. Like, for instance, what is the cheapest cost I can build this fence for if the length is made of plywood, which is $10 per yard, and then the length or the width is made of oak wood, which is more expensive, $20 a yard. And so we're going to basically see how cost is going to affect our optimization problems. It definitely makes it more difficult. We'll find that out soon enough. So thank you all for watching. If you have any questions, please post them in the comments. Have a great rest of your day, and I'll see you in the next video. Take care, and bye-bye.